So in this chapter, we're going to be talking about electrochemistry, and the first half of this chapter is going to be on how to balance redox reactions in both acidic and basic solution. So just as a quick review, let's just see here. As a quick review, okay, electrochemistry is first introduced in Chem 130 and Chem 151 with the idea of redox reactions. And redox reactions are really two half reactions where you have a reduction, which is a gain of electrons, and an oxidation, which is a loss of reactions. And in a lot of classes, we often use this LEO goes GER, and basically LEO means the loss of electrons and gain of electrons. And then the O stands for the oxidation, and the R stands for the reduction. So LEO goes GER, the loss is an oxidation, the gain is a reduction. In this chapter, we'll be examining redox reactions and balancing redox reactions that occur in acidic or basic solutions. And just remember that the idea of balancing reactions is we're going to have the same number of elements of each kind and in each side of the arrow in the reactants and in the products. So I want to just really quickly review how we do notations. As a side note, remember that in the acid-base chapter, when we were talking about a strong bronzocellularic acid placed in solution, it actually disassociates. So if you have something like HA, where HA is the acid, if you put it in water, it will fully disassociate into H plus and OH minus. And then, of course, the H plus immediately reacts with any water because it's in aqueous solution. And, of course, it will form H3O plus. So really there is no H plus in solution. There's only H3O plus in solution. However, writing H3O plus every single time is very time consuming. So really, we just like to write H plus instead of H3O plus, but we do know that H3O plus is really what is in solution. Now, that's what we mean by saying in reality there is no proton or free H plus in solution, as it immediately converts into H3O plus. So that's what we're saying here. And as a side notation, it is easier to write H plus, so we're going to write H plus even though we really do mean H3O plus. All right. So we're going to look at some skeleton oxidation reduction equations that are necessary to tackle more complex reactions. And the three things that we're going to be considering when we're balancing oxidation reduction reactions is what species is being oxidized, what species is being reduced. And remember, what is being oxidized is always the reducing agent because it causes the reduction of the other species in the solution. And what is being reduced is always going to be the oxidizing agent because it itself is reduced, but it forces the other species to be oxidized. So it is the oxidizing agent, but it itself is being reduced. Okay? And we're often considering, of course, what species is the result of the oxidation and what species is the result of the reduction. Okay? And of course, in this chapter, we're going to be looking at whether it occurs in acidic or basic solution. And I'm going to teach you how to deal with acidic solution first and then basic solution afterwards. So I think a very generalized reaction I think would be good to look at would be, let's say, if we had Mg0 becoming Mg2+. Okay? And really, we're going to think about it and go, how did Mg0 become Mg2+? Well, it did become Mg2+ because it lost 2 electrons, or it got separated from its 2 electrons, okay? Which really means that these 2 electrons have been lost, okay? Another way to look at this pictorially is to go, okay, here's Dr. Chang, okay? And what happens after the reaction? if you look at this reaction, you'll see, okay, this means that this person, Dr. Chang, has lost her head, okay? Or this head has been lost, okay? So we always write the thing that is lost on the right side of the arrow. Or the reaction arrow is what we're thinking, okay? It's always on the right side, okay? And when things are lost, remember we said Leo goes Gur, so loss of electrons is oxidation. So the loss of electrons is really oxidation, okay? So this reaction that I've written here, Mg0, neutral, becoming Mg2 plus, okay, and 2 electrons, is a half reaction that represents a loss of electrons, or what we call an oxidation. Okay, let's look at another example. Okay, let's say that you have 2 H pluses and they become 2 H neutrals. Okay, how did this happen? This happened because each H gained 1 electron. So let's think about it. If you had 1 H, I'm going to write it up here, and you gained 1 electron, okay, it becomes H neutral, right? Okay. If you're not sure, you can always do math really quickly. You can say H plus and minus. When you add those two charges together, it becomes neutral. Okay, just like math. If you think about it this way, is like plus, 1 minus, and you think of the arrow as an equal sign, equals 0. If you add these two things up, right? 1 plus, 1 minus equals 0. So if you have 2 of H's, if you have 2 of these, each one needs to gain an electron. So overall, there is a gain of 2 electrons. But each hydrogen gains 1. Okay? So then you have the result of 2 hydrogen neutrals. Okay? So when we have a gain of electrons, we will always write it on the left side of the arrow. Okay? And E minus does stand for electrons. So when it is on the left side of the arrow, it is gained. Okay, and again, I have a little cartoon to remind you of how to remember this. If you had Dr. Chang and she ate a donut, okay, what happens when you eat a lot of donuts? You become a large Dr. Chang, right? Okay, so this donut is being gained by Dr. Chang. Okay, so remember it's on the left side of the arrow, so it is being gained. Now, when you say a gain of electrons, it's a reduction. So we say GER, gain, electrons, reduction. Okay, so this stands for a This half reaction stands for a reduction. Okay. Now, if we have these two reactions in a container or in a system, okay, oftentimes they will drive one another. What we say is Mg will lose 2 electrons, and where do those 2 electrons go? They will be gained by the 2 H pluses, and so therefore these two will cancel out left and right, just like when we were looking at Hess's law in 151. And so we just bring everything down. What is on the left side of the arrow is Mg0 plus 2H pluses gives you Mg2 plus 2H zeros. This is what we call a balanced half reaction. Okay, there are the same number of magnesiums and hydrogens on each side, and in addition, there's the loss of 2 electrons and the gain of 2 electrons. So the loss and the gain of electrons must be equal on both sides. This is what we learned in 151 when we were talking about skeleton oxidation reduction equations, and we're going to be looking at these in more detail in this chapter. Okay. So some rules to remember in terms of how to basically assign oxidation reduction charges. So when we're looking at oxidation numbers, or how do we determine what is the oxidation number? The first rule is that if it is elemental, the charge is, or the oxidation state is always 0. Okay? If there's only one kind of atom present, that means it is elemental. Okay? Now, it's very interesting because things like S8, okay, there are 8 sulfur atoms bond together, but they all carry an oxidation number of 0, okay, because there's only one kind of element, one kind of atom present, and that is the sulfur, okay. Oftentimes we'll write things like iron solid, okay, or carbon solid, copper solid, okay, H2 gas, okay, oxygen gas. All of these, because there's only one kind of atom present, they all carry a charge of, or an oxidation state of 0. Okay. Now, if you have a monoatomic ion, meaning that it is an ion and is indicated as an ion, then the oxidation state matches the charge. So if it's F2 minus, then the oxidation state is 2 minus. If it's Fe2 plus, then the oxidation state is 2 plus. That's very straightforward. If it's in the group 1 metals, i.e. what we call the alkali metals, so these are things like lithium, sodium, potassium, okay? When in a compound, they all carry charges of plus, right? We think about NaCl, Na is plus, Cl is minus. So because they're all plus, they should have a charge of plus when it's a compound. Okay. Now, when it is elemental, remember, go back to rule number 1, it is neutral. So let's look at an example. Li solid. Because it is not a compound, it is Li neutral. But if you have LiCl in a compound, then the Li is positive because the Cl is negative. Okay? So when it is a group 1 metal, it is 1 plus, unless it's elemental. And as an extension of that, if it's a group 2 metal, group 2 is the alkali earth metals. These are things like calcium 2 plus, magnesium 2 plus. Okay, these ones we know they're in the second column. They are 2 plus, unless again elemental. And again we say calcium is 0 if it's a solid, but if it is calcium chloride, then it is Ca2 plus, and each Cl is minus. Okay, so we say each Cl, or 2 Cl minuses. Hydrogen has 2 possible oxidation states. It is 1 plus when it is bonded to a nonmetal. It is 1 minus when bonded to a metal. Okay, and again, just think of a very easy way to remember this. If you have HCl, Cl is a nonmetal. So again, Cl is Cl minus. So H has to be what? H has to be H plus. Okay. The reverse of that would be if you had something like NaH, or sodium hydride. H is a, Na is a metal. Okay. And so Na, we all know, is Na plus. That means that H must be H minus, or what we call a hydride. Okay, so depending on what it's paired with, if it's paired with a nonmetal, it's always plus. If it's paired with a metal, it's always minus. So I would just like keep these two as examples, so that when you encounter an H, you can pull up this example in your head to remember what is the charge on H. Okay, oxygen has 2 possible oxidation numbers. It is 1 minus if it's in a peroxide, O2 2 minus. then in all other compounds, which is most common, it is 2 minus. Okay, so something like H2O, you would have, let's do it here. If you have H2O, because each hydrogen is 1 plus, okay, so that's 2 plus total, right? This oxygen, there's one of them, it must be 2 minus for it to be balanced, okay? But if you have something like H2O2, now it's different. This is hydrogen peroxide. Again, hydrogen is 1 plus and 1 plus, okay? But because there are two oxygens, each one must be 1 minus because there are 2 of them. So in this particular situation, each oxygen is 1 minus. So we say O minus, okay? Or there are 2 of them, so 2O minus. This is only for things like peroxides. And on the homework, you just have to be very careful. And if you notice H2O2 or Na2O2, then you have to realize it's a peroxide. All other ones, oxygen is 2 minus. The oxidation of fluorine as the most electronegative is always 1 minus. Other halogens in this chapter will carry all kinds of charge depending on what it is bonded with. Okay. Rule number 8 and 9, saying that the sum of the oxidation numbers of all atoms is neutral in a neutral compound, and the sum of the oxidation number of all atoms in a polyatomic ion carries the charge of the polyatomic ion. We're going to apply these 2 rules, and we're looking at the actual problems. So just hold on. If you're not sure what this means, we're just going to apply the rules as we go along. All right, so let's look at the first example and how we're going to apply all of these rules to balance an equation. And remember, we're trying to balance the equation, and it is in acidic solution, so you should end up with H plus, okay, to balance out the hydrogen count because it is an acidic solution. Okay? And remember, when we're balanced, we know that it's balanced because 1, loss of electrons is going to equal the gain of electrons, and 2, number of atoms in products and reactants are the same. Okay, so if you have 10 hydrogens on the reactant side, you must have, say, 10 hydrogens on the product side, and so on and so forth. All right, so let's look at the example. This is example from your textbook. I believe it is example 19.1. Let me just check real quick. I'm not sure. But anyway, it's an example from your book. And so they're saying Fe is 2 plus, Mn is 7 plus, Fe is 3 plus, and Mn is 2 plus. Okay, just as a quick review, remember these are all monoatomic. So Fe2 plus is monoatomic. So it carries the charge. Fe3 plus is 3 plus, Mn2 plus is obviously 2 plus. But let's look, how did MnO4 minus the Mn is 7 plus? We're going to apply that rule that we're looking at, rule number, the last rule, in that oxidation reduction page. And we're going to look at it real quick. Let's just look at it real quick. It says the sum of, rule number 9, the sum of the oxidation numbers of all atoms in a polyatomic ion is equal to the charge on the polyatomic ion. So we are looking at a polyatomic ion, right? MnO4 minus. So let's do it really quick on this on the side here. MnO4 minus. Okay. Remember, oxygen, each one is 2 minus, and there are 4 of them. So really, we have 8 minus. Okay. And you have an overall charge of minus. So you must have it equal to 1 minus. So what must Mn be to make this true? Mn must be 7 plus, right? 7 plus 8 minus is 1 minus. So this Mn is 7 plus. To make this polyatomic charge ion makes sense. That's how they got the 7 plus here. Oftentimes, I will write the oxidation numbers in little circles under each of the elements. So in the homework key, for example, you'll see me write the oxidation of each oxygen or each manganese or each whatever element I'm looking at in little circles. And remember, it's not the overall that I'm writing. The overall charge is going to be underneath that circle, but really the oxygen carries a 2- charge and manganese carries a 7+ charge. So let's look. Okay, step 1 says to assign oxidation numbers to each atom. So we've done that. Okay, and so that way we can tell what is oxidized and what is reduced. 2, we're going to split the skeleton equation into 2 half reactions, proceeding as follows. Note the species containing the element that increases in oxidation number and write those species to give the oxidation half reaction. Similarly, note what species containing the element that decreases in oxidation number and write the reduction. So basically what they are saying is you're going to write 2 equations, okay? So the first equation that we're going to write is, let's say our Fe. Fe started off as 2+, and it became Fe 3+. The only way this is going to happen is if you lose an electron. And we know it's a loss because it is on the right side. How did I know to write it on the right side? I just looked at the number, right? 2+. If you think of this arrow as an equal sign, okay, then if you think of this as an equal sign, 3+ plus 1- equals 2+. Okay. Then again, we're going to write another equation for the gain of electrons. Okay. So again, we're going to start off with my Mn. My Mn 7+, and it becomes Mn 2+. And again, if you think about it, you've got to write 5- on this side to make this true, right? 5- plus 7+ gives you 2+. And because the 5 electrons are on the left side, it is a gain of electrons. Okay. Now notice, they're not balanced in terms of the loss and gain of electrons, right? We would like to balance so let's look at it. Let me just read step number 3. We need to complete and balance each half reaction. Balance all atoms except O and H. Balance oxygens by adding H2O. So we don't have any oxygens or hydrogens in this particular example, so we're going to ignore that for now. We can balance hydrogen atoms by adding H+, and again, we're going to ignore that for now. But we do need to balance the electric charge by adding electrons to the more positive side or the more side that's lacking electrons. So let's look. There are 5 electrons being gained. And here there's only 1 electron, so we need 5 here. The only way to make that 5 is to multiply this whole equation by 5. Okay? 5, 5, 5. Because each iron loses 1 electron. So if you have 5 iron atoms, you're going to lose 5 electrons. Okay? If you don't get that, then listen to that again. Each iron atom loses 1 electron. So therefore, 5 irons will lose 5 electrons. So the nice thing about that is then, if you lose 5, where do those 5 go? They're gained by the manganese if they're all sitting in one redox system. Okay. So then step number 4 says to combine the 2 half reactions to obtain the final balanced oxidation reduction equation. So we're going to do that. Okay. We're going to combine these 2. Okay. So therefore, we're going to say 5 iron 2 pluses. And oftentimes I like to bring down the arrow first. And you have 1 manganese 7 plus, okay, is equal to 5 iron 3 plus and 1 manganese 2 plus, okay? And so we're just going to read step 4. It says multiply each half reaction by a factor such that when the half reactions are added, the electrons cancel. We've done that already. 5 electrons lost, 5 electrons gained. Simplify the balanced half reactions by canceling the species that occur on both sides, and reduce the coefficients to the smallest whole number. In this particular case, the coefficients are already the smallest, and there are no redundant species, so you can just stop there. Okay, so this is balanced in terms of the acidic situation. Okay, now the last thing that you need to do, and I like to do this last, but you can do this first if you want, is really keep track. The Mn7 plus is really, I'm going to erase this real quick. This Mn is actually really MnO4 minus, right? It carries a charge of 7 plus. I'm going to write that really high up above it. Okay? So really, what we're going to do is we're going to just really quickly rewrite this equation again and balance it completely using the full step 3. And you'll see what we're going to do in just a second. Okay? And apply the rule in step 3. Okay? Step 3 says to balance oxygen atoms by adding water. So because there are 4 oxygens here, we're going to write, I'm just going to erase this real quick. We're going to write 4 H2Os. Okay? So now there are 4 oxygens and 4 oxygens here, right? Okay. Now, we also need to balance the hydrogens. There are 4 times 2. So here, I'll show you. 4 times 2. So this is really 8 hydrogens, right? So really, we need to balance hydrogen atoms by adding H plus ions. So we're going to, I'm going to run out of space here, but we're going to write H plus. And we do have 8 H pluses here, okay, on the left side, okay? So let's bring everything down again. So we're going to have a final answer of 8 H pluses plus MnO4 minus gives you Mn2 plus 4H2O. Okay? Last but not least, to be very clear, this is aqueous, this is aqueous, this is aqueous, and water is always liquid. Okay. So now it is balanced, and because it is in acidic solution, okay, we can stop here with the 8 H pluses because it is an acidic solution. Now, if it is in basic solution, we're going to have to do one more step, but we'll get to that when we get to the basic solutions. Okay, let me do one more example, and then I'm going to, let's just do another example real quick. All right, so you've got elemental zinc, and it reduces nitrate ions to ammonium ions. Okay, so what we're looking at is we need to write down what equation is happening. So we're going to write this equation here. We've got our zinc, okay, elemental, and elemental zinc has to be solid, and it reduces nitrate. Nitrate is NO3 minus, okay, that's aqueous, okay. It reduces it down to ammonium. Ammonium is NH4 plus, and that's aqueous. And of course, zinc is oxidized to zinc 2 plus, and again, that is aqueous. Okay. What I often like to do is underneath, just really quickly, write the oxidation states, 0. Okay. Now, zinc here is also 2 plus. Now, the other ones are a little bit more difficult. So let's look. If each oxygen is 2 minus, and there are 3 of them, because it's NO3, that's 6 minus. And it equals 1 minus. So the only way this is true is if there is 5 plus on this side. So this nitrogen is actually 5 plus. Okay? Then, of course, this hydrogen, remember nitrogen is a nonmetal. I repeat again, nitrogen is a nonmetal. So that means that H is 1 plus, according to our rules. Okay, and there are 4 of them. So 4 plus equals the overall charge of 1 plus, because it's NH4 plus, that's the overall charge. So therefore, this nitrogen must be 3 minus. Okay? So once I have calculated this, oftentimes you'll see in the book they write the actual oxidation state as a number like this. Okay? So this really helps because what you're going to do is you're going to write just the basics. Zn is changing. It is becoming Zn2 plus. Okay? And NO3 minus is becoming NH4 plus. Okay? And let's look at our electrons. We've got our 0, 2 plus. The only way this is going to be true is if it is 2 minus here or 2 electrons. Nitrogen is plus 5. Okay? Nitrogen here is minus 3. The only way to make this true is to add 8 electrons, right? 8 minus plus 5 gives you 3 minus. Okay? Hopefully you're still with me. Okay? Next, we need to consider the hydrogen and oxygen count. So let's look at that real quick. Okay? In the zinc equation, there is no hydrogen and nitrogen, so you don't need to worry about it. But in this particular case, there are 3 oxygens on the left, so you need to add 3 waters. Remember, when you balance oxygens by adding waters, right? So 3 oxygens, 3 oxygens, okay? But now that means that there are 4 hydrogens here and 6 hydrogens. This is 4, this is 6, or 10 hydrogens on the right side. So you need 10 H pluses on the left side. Okay? This is good. Okay? One more thing we need to do. Let me just write these 10 hydrogens down low so I know that it's part of that second equation. 10 H pluses. Okay. Last thing we need to do is to figure out the number of electrons. So here there are 8 electrons on the left side, and here there are 2 electrons. The only way to balance it is to have 8 electrons on the right side as well. So we're going to multiply the zinc reaction, okay, by 4, because if 4, and 4 times 2 is 8, right? 4 times 2 is 8. So really, that means that your electrons cancels out. Okay, it brings everything back down. So now let's bring everything down. You've got your 4 zincs. Okay, you've got your 10 hydrogens. Oh, already 10. You've got your NO3. Okay, and this gives you zinc 2 plus NH4 plus ammonium plus, and around the space I write it here, 3 H2Os in liquid. Okay, and if you want to check really quick, because we are balancing, you've got 4 zincs, 4 zincs. Oops, I don't have 4 zincs. There we do. 4 zincs and 4 zincs. You've got 10 hydrogens and 10 hydrogens. You've got 1 nitrogen, 1 nitrogen, and you've got 3 oxygens and 3 oxygens, so it is balanced. Okay? And again, it's an acidic solution, so because you have H plus here, it is acidic. Okay. Shall we do one more example really, really quick? Let's see here. This one, okay, this is example 19.1 from your book, okay? And so we're going to do I2. I2, remember, is elemental, so let's write down what we know. I2 is elemental, so it's 0, okay? The other ones are not 0, but we do know that oxygen is 2 minus times 3. That gives me 6 minus. And because there's a negative charge there, it must equal 1 minus. So this must be, again, 5 plus. So really, it's plus 5. Okay? Here, oxygen is, again, 2 minus times 3 is 6 minus. And it, again, is equal to 1 minus. So this iodine, okay, must also be 5 plus. So we're going to write 5 plus here. Okay. Last but not least, this oxygen is 2 minus. There are 2 of them. So really it is 4 minus. So remember here there is no charge. So it's neutral. So it must equal 0 because there is no charge. So the way it's going to be balanced, if it's a 4 plus, so this nitrogen is 4 plus, and oftentimes we'll write it here 4 plus. All right. So this allows us to know what is oxidized and what is reduced. Okay, so let's write it down. Iodine, oops, sorry about that. Iodine is 0. Okay, I'm just not going to write the states until the very end. It'll make it a little easier. Okay. And it becomes iodine let's do this. Iodine is plus 5 and 0 here. Okay, the only way to make this statement true is if you added 5 electrons on this side. Okay, then you've got NO3 minus, and it becomes NO2, no charge. So again, let's write it down. NO3 minus is plus 5, NO2 is 4 plus. And the way this works is if you had an electron on this side. Oops, let's make it black. So 5 plus 1 minus is 4 plus. Okay. The next thing we should really do is consider the oxygen count. Okay. So there are 3 oxygens here. So we're going to write actually, let's do the oxygen count at the end. It's easier to do it at the end. Yeah, let's do that at the end. So let's do this. We've got 5 electrons here. We've got 1 electron here. We need to multiply this by 5. 5 and 5 so that everything is balanced that way. All right. So now let's bring everything down. Okay. So these cancel out. Make a mistake, you just start over. No problem. Okay. So actually, this is actually a good point to make because each iodine let's do this here. Start over real quick. Apologize about that. Okay. So each iodine gains 5. So if you have 2 iodines, you actually gain 10 electrons. Each one gains 5. You have 2 of them. You gain 10 electrons. This is still 1 electron. 5 plus 1 is 4. But now because there are 10 electrons on this side, we have to have 10 electrons here. So we need to multiply by 10. 5 becomes 10 and 10. I apologize. Okay. Then these cancel out. Okay, and we're going to bring everything down again and recount. Okay, so let's count again our oxygens. So 10 times 3 is 30 oxygens. 2 times 3 is 6 oxygens. And 10 times 2 is 20 oxygens. So this comes out to 30 oxygens on the left and 26 oxygens on the right. So I need 4 oxygens, so we need to add 4 waters. Because we need 4 more oxygens. So 4 waters. Then let's count our hydrogens. Our hydrogens is 4 times 2 is 8. And we don't have any on the left side. So we need to write 8 hydrogens on the left side. Okay, so that gives us final answer 8 H pluses plus I2 plus 10 NO3 gives us 2 IO3 plus 10 NO2 plus 4 waters. Okay, so that is our final answer. And that all happened because there are 2 iodines here. There must be 2 iodines here. Okay, so when you're doing the homeworks, don't do the mistake that I made and then caught myself on. Make sure that you balance at the beginning before you start doing all the oxygen and hydrogen counting. All right, I'm going to stop the video here and go ahead and do the homework problems for all the acidic solutions and then watch the next video for the basic solution.